Hello everyone, my name is Tanuj and I graduated from Bhagwan Parshuram Institute of Technology, which is part of the Guru Gobind Singh Indraprasth University, Delhi in 2020. And today I am going to be presenting a paper titled Facial Expression Recognition Using Landmark Detection. So let's dive right into it. So first I'll talk about what motivated us to take up this problem. So as you know that recognizing the emotion of a person is a really important problem, simply because like even without communicating we can tell by seeing the face of a person whether they are happy or sad, or maybe from their tone or language, or maybe whatever like text they have written, right? So now that we know that it's an important problem to solve, there could be various sources to solve this problem, right? Maybe you could solve this problem using the images, using the speech, using text, right? So why did we go ahead with images? So this is because like there are a lot of images available on the internet due to the digital era. Since these machine learning, deep learning algorithms require a lot of data to perform well, we thought of going ahead with this approach as compared to other data sources. And the application in service robots, in driver fatigue monitoring, in intelligent teaching systems. So let's talk about the related work, like how people solved this problem before us. So traditionally, what people used to do was they used to handcraft features from the images. Like a person would actually sit down and manually handcraft features from the images. Like they would see, like what are the corners of the eyes, what are the corners of the nose, what are the corners of the lips, and then they would feed these handcrafted features to a machine learning algorithm that would tell us what is the emotion of a person. So in order to eliminate this, what came was the deep learning era, in which there is no need to handcraft these features. We can just like given the image to the network, and the network can automatically extract features from that image, right? So these deep learning networks usually work well with images, but still there seems to be a missing piece of information here that we attend to in our work, that we should only focus on the important regions of the face and not everything, like the forehead, the ears, the region below the chin, the hair. They do not contribute important information towards the emotion, right? So the dataset we used for this was the Jaffa datasets, which consist of 7 facial expressions, namely happiness, anger, disgust, fear, surprise, sadness, and neutral. And the size of each image was 120 cross 128 with 213 images in total, around 30 images for each network. So the network we used was the convolutional neural network, which actually emulates the human brain to predict the emotion. So the main components were convolution operation, maximal operation, flatten layers, dense layers, and dropout, which we used in a network. So this is basically a convolutional network which predicts what digit we have over here. So if it's a 4, uh, we would have like a bullet against a 4 here, and and rest all will be 0, right? So the digits are from 0 to 9. So what it does is it just takes little by little region of the image in every operation, performs some mathematical operations, and gives us the result. So I'll dive into convolution operation now. So what is a convolution operation? So convolution operation basically uses a filter, which is the blue one which we see here, and shadows it on the input image, right? And predicts and performs some mathematical operation and gives us a value here. So we apply this filter repeatedly depending on the input agent, depending on the stride, right? And then we populate this thing called a feature map, right? So this is basically the convolution operation. What it helps us to do is that it helps us to extract information from the image itself. So if we could have a filter, say, which gives us the vertical lines in the image, so in the whole learning process we try to figure out the optimal parameters for this filter. Next comes the maximal operation, which is basically a downsampling operation, which is used to decrease the size of the input in like the cool down the network, because the network may become a lot more like complex with a lot of parameters. So we need to cool down the network. What we do is, like, if we perform a maximal operation between these 4 numbers, we will actually place the maximum value. Like we can also have a min pool, right? So this was the network we used. We give our network a input image of size 128 cross 128, and then we perform convolution and maximal operation. And so these are the two operations which we perform 3 times. Then we flatten our network, then we perform a dense layer, then drop out, and then we finally get an output of size 1D vector 1 cross 7, right? So now that we know about our network, we use a thing called landmark detection using OpenFace. There's a need to remove less important information like ears, hair, and background. As you can see that we have removed ears, hair, and background using a open source tool called OpenFace, which is capable of like real-time performance, simply using a webcam without any specialized hardware. And you can read up more about OpenFace, like how it works. So basically it uses neural architectures plus a mixtures of expert networks. So now let's talk about the big picture, how we perform the whole process. So first we parsed our data set, applied OpenFace on those images, right? And then we collected that transformed data, pre-processed those images, like perform resizing, normalization. Then we did a train test validation split. uh, then we trained the model, then we evaluated it, and finally we tested our model. So now let's talk about the experiments we performed. So we kept the architecture same for both the experiments. One was with the landmark detection and one was without it. And we trained the model for 50 epochs. We initialized the weight with a Colruyt uniform initializer, used an ADAM optimizer with a learning rate of 0.001, and we had a 120 is to 29 is to 43 split for training, validation, and testing respectively. So as you can see, the accuracy considerably improved with landmark detection, and the aim here is to show that this landmark detection really works, and not compare this our work with state of art, because you could like build a more sophisticated network any day and achieve better accuracy. But the aim is to show that landmark detection really works, which can be used in real-time systems. Right. So this is the model loss and accuracy for our two experiments. So you can see that the loss and accuracy considerably improved. So the first row is for the first experiment, this for the second experiment. So some lines of the future work could include making the network more sophisticated, right, to achieve a better accuracy, and maybe use attention convolution, which focuses on the salient regions of our face. And we can also use region attention networks for tackling pose and occlusion. Thank you everyone.